Tuan. The title is Linear Algebraic Abduction with Partial Evaluation. We start.
Yeah, thank you for your introduction to my talk. So hello everyone, my name is Tuan. I'm from NAI, and I'm glad to be here today at my first time at PADL to give my presentation of our work in collaboration with Katsumi Inoue sensei and Professor Katsumi Inoue and Professor Chiaki Sakama. The title of my talk today is Linear Algebraic Abduction with Partial Evaluation. So my talk today is divided into 5 parts. The first section I will give an overview about the propositional Horn abduction problem and some definition that we use throughout the presentation today. And in the second section, I will quickly give an overview about our method, linear algebraic computation of abduction. And in the third section, which is a main contribution of our work, is we present about the partial evaluation in the language of linear algebra. And finally, we will demonstrate our result in the fourth session. And in the fifth session, we close my talk today with conclusion and discussion. So let's move on to the first section. As you may know, abductive reasoning is kind of inference to the best explanation, starting from the observation. So, for example, here, if we already know that weather makes things wet, and rain is a source of water, and if we see the grass is wet, so we may conclude that it was rained maybe a couple of hours ago, something like that. And abduction has so many applications in model-based diagnosis, belief revision, and automated reasoning. And abduction is an active research, and recently gained more attention in building explainable learning models. And this is a quick definition of the propositional Horn clause abduction problem, which is PCAP in short. A PCAP can be modeled as a quadruple LSOP, where the L is a set of own propositional variables, and S is the set of own hypotheses, and O is the set of observations, and P is the logic program, which is a set of Horn clauses. And the goal here is to find the set of minimal explanation that satisfy the following explanation definition. So a set E is an explanation if of the PCAP if and only if the set E together with the theory P is consistent and also entail the observation set. And an explanation E is minimal if there is no smaller, which is not no subset of it, is also another explanation. So this is an example of the PCAP problem. We have a simple program like this. So we have the LSOP is like this, and this is a set of the rules. So we have the N rules, all rules, and this. The set of minimal explanation is here, H1, H3, and H2, H3. And deciding if there is a solution of the PCAP is an P-complete problem. And in this work, we focus on the PCAP with the program is an acyclic program. And for convenience, we partition the program into the N part and the all part. So which is respectively the set of N rules and all rules in the format of this. And we call a standardized program is a definite program such that there is no duplicate head item in the program. So we assume that the standardized program have no duplicate head in the item, so that we can have kind of an all graph of the program. So for example, to continue the previous example, we can draw a graph look like this. When green node here are the N node, which equivalent to the N rules here, and the yellow nodes here is the equivalent to the all rules here. So let's move on to this next section. So first I want to introduce the definition of the program matrix of the pickup. So let's P is a standardized program of the pickup problem, and then the P can be represented by a matrix following this definition. So it's simple, just like for n rules, we set a value for each element of the rules by 1 divided by the number, by the length of the root. And for the all rules, we set 1 for each propositional variables appear in the body rules. And this is for the fact we set 1 at the diagonal of the matrix. And this is our update compared to the previous definition of the previous work by Professor Sakama et al. We set also the for abducible propositional variable as 1 at the diagonal, and we set 0 for otherwise. And any Horn program can be transformed into a standardized program in linear time. So the basic step is that we have the Horn program, we standardize it, and then we convert it into a matrix. So this is an example, the previous example actually. So this is the program matrix of this program. So the first rule here equivalent to the first row of the matrix, and this one is the fourth row of the matrix, and these 2 rules here is the second and the third row of the matrix, and so on. So we also define an abductive matrix. So it's just simply the transpose of the program matrix. So we take the program matrix here and we transpose it. We obtain the abductive matrix. And for every subset of the set of the propositional variables here, we can represent it by a vector. So for example, here this is a vector of hypothesis. So for each element appear in the set, we set 1. And similarly, we have the observation vector here. And a linear algebraic computation, in short, can be a set of transformation converting observation vector into a vector representing a subset of the hypothesis. And each transformation step is a single step abduction. And we refer to the vector representing the explanation as an explanation vector. An explanation vector reaches an answer if it is the subset of the hypothesis. And if the explanation vector V does not contain any head of the all rules, so the abduction step is relied by the matrix multiplication with the abductive matrix. So this is the abductive matrix, and by multiplying with the observation matrix, we obtain the explanation of it. So we say that to explain P here, we have to explain both the Q and R. And we also have initial condition that we set the summation of all elements appear in the matrix here is 1. So a vector is unexplainable if the summation of all elements here is less than 1. If the explanation vector contains head of any all rule, abduction step is relied by solving a minimum set problem. So this is this problem is kind of we have a set, a family of set, and we find the set that intersect on the set of the family. At least one has the same. So for example, here we have these 2 rules with 2 all rules here, and we take this body of these 2 all rules at the input for the minimum hitting set solver, and we solve this problem. We obtain the S hit on the 2 set here, or S1, S2. This set also hit on the 2 set here. So we say that to explain Q and R, we either need to explain S or to explain both S1 and S2. So based on that, we define the condition, which is all computable and computable, which is simply based on whether the rules contain the head of all rule or not. And for n computable vector in matrix, we can compute the explanation by performing the matrix multiplication as I showed before. And also for the all computable vector matrix, we can find the explanations by enumerating the minimal hitting set. So next, I talk about the partial evaluation. So we consider a more complicated example. Here we have a P-cap, LSOP like this, and a program like this. Note that here the program is not standardized because we have two rules with the same head. So first we standardize by simply put a new body for each rules here, and we put an all rule in the new program, and then we transform it into this new rule, two rule here. And so the NO graph of this program P prime can be represented by this graph. And we can obtain this one is the abductive matrix of the program. So here we have the green column as n rules, and the the yellow column here is all rules. And then we take that matrix to solve the problem. So we take the observation vector, we multiply it with the abductive matrix, we obtain explanation of this. And we also, I should note that the vector matrix can be represented in sparse format, which is maybe COO or CSR or CSE format, but maybe I have no time to talk about this. So in the next iteration, we continue to multiply it with the abductive matrix, and then we obtain this matrix. But here we have the matrix with the head of the all rules, which is E2 here. And then now we have to solve the minimal hitting set problem. We take the body rules of the E2, X1, X2, and we solve it. We obtain the next matrix. And this is the next matrix. And this one is n computable matrix, so we can continue to multiply with the abductive matrix, and we obtain this matrix. And in the next iteration, continue with, and here we obtain the final step that we reach on the hypothesis, the subset of hypothesis set. So the algorithm stopped, and we found these explanations, H1, H2, and H2, H3. So can we do better? We take fourth iteration. So we propose partial evaluation to do it maybe in better way. So first, I introduce the definition of reductive abductive matrix. So we can obtain the reductive abductive matrix by just simply take the abductive matrix and remove all the column with regard to the all rules in the program, and setting the one at the diagonal corresponding to the head of the rules. So for example, in the pivots rule, we have E2 here, we have X1 and X2, but now we remove that value here and we set 1 here. So this one is a partial evaluation of the abduction. So in this, we have a P-cap, and the program is in standardized format. And for any n rules in this form, if the body contains an atom bi, which is not the head of any rules in P, then we just remove it because we have no way to explain the rule. And that's why we, for each atom appear in the body, if we have another n rules of it, we then replace the conjunction of the body rule then to the rule R. And the resulting rules is denoted by unfold R, defined as follow. So P EVA is called the partial evaluation of the program P. So consider the example. So it's actually the pivot example. And we have the set of rules, the P prime here. And unfolding rules, like we will take the first rule here and we see the E1 here, and we look after the rule E1 and we replace this body to this R1, and we have this rule. So and so on. We can do similar thing with this rule, and this rule. But for this one, we have no way to unfold it, so we keep it as the original rule. So finally, we got this one is a partial evidence of the program. And actually, we can do it in the linear algebraic way by computing the power of the reductive abductive matrix. So it simply just, we take the reductive abductive matrix I defined before, and we compute the power of it, and so on for k step. For example, like we power it for k power 2 for k times, and this is a graph representing this matrix. It's actually the original graph, but we just remove the add from this all rule from E1 to X1 and X2, and by computing the power of the matrix, we can visualize its effect, like we connect the node that we have the way to each other, and we squeeze out the graph and connect it directly to the node that we have the path inside the graph. And so on, we do the same thing. So it becomes like a b-party graph. And here we reach a fixed point at the k equal to 2, and we refer to this stable matrix as a P over P and take it to solve the P-cap problem. So we do the same thing with starting from the observation matrix. We multiply it with the P over matrix, and we obtain this matrix. And here we have the head of the all rules, and then we have to solve the mean reckoning test problem. But this problem is different from the before problem. So we do the same thing, and we got the next matrix. This one is the next matrix, and this one is uncomputable, and we can also compute again, multiply it again with the partial evaluation matrix, and we obtain this matrix. And here is the algorithm stop, and we found the minimum explanation. We actually see that the result is the same as before, but we only take 2 iterations rather than 4. So partial evaluation is repeatedly performed as like we unfold the rules until we reach a fixed point. And it also can be realized as computing the power of the reductive matrix, reductive abductive matrix, something like this. And the partial evaluation also has a fixed point. This one has been proved in our paper. And the k-step partial evaluation has an effect of realizing 2 power k-step deduction at once. So multiplying an explanation vector and the partial evaluation matrix realize exponential speed up. However, computing the power matrix is quite costly, so we need to verify the positive effect can win the trade-off. So in the next section, we will show the performance of our method. So we do experiment on the FMEA-based benchmark dataset by Koy-Histov and Kotawa, which has been used in their paper. So it's including 3 benchmark datasets. And the first one is deeper but narrower graph structure. And the second one is deeper but wider graph structure, involving some like many large number of medium-sized medium reckoning size problem. And the third one is shallower but wider graph structure, involving a few but very large size medium reckoning size problem. So we implement our method as 2 versions, dense and sparse version, using Python, NumPy, and SciPy. Each version we have one with partial evaluation and one without partial evaluation. And for large size, we use a PSAT. We also have our own way to solve the minimally test problem, but of course it's not good as compared to PySAT. And we also have demonstrated our performance of the method, of our method, with other symbolic approaches in our paper at the ICTAI. Our method is comparative with the other symbolic method. So in this paper, we only compare our method, but actually the result here can compare directly with the previous paper. So this is a result with the original benchmark. So maybe I should show the detail table here. So in overall, all the method can solve all the problem in the data set. And partial evaluation improve much more performance with the two data set here. So here we record the number of solver sample, the number of fastest sample. T plus TP here is time, such as the effective solving time, and the penalty time, which is 20 minutes if the solver cannot solve the problem. So it's like the part 2 in SAT solver. And this is TP eva, which is the time we compute the power of the reductive abductive matrix. And so we also see here the performance, the degradation happens in example artificial symbol 1 for both dense and sparse method, which is here like very slow compared to the version with without the partial evaluation. So in the we try to improve to enhance the benchmark data set to show our performance better. In this experiment, we enhance our benchmark data set based on transitive closure problem, and we generate a p-graph based on a single line graph like this, and then we consider the observation to be the path 1 to 10 and look for the explanation of it. And next, for each problem instance, we find the rule here in the form of this, and then we append this problem into the each instance here with a probability of 20%, and the resulting problem is expected to have the subgraph of n rules occur more frequently. So this is the next the result of the enhanced benchmark dataset. So we can see now the runtime trend here is for maybe it's a little bit tiny, better for the sparse matrix with the PADL' method, but we should see the detail table for more detail. So with the enhanced dataset, we now see the partial evaluation can improve the performance for sparse method significantly in this sample. So this is better than 16,000 milliseconds. However, the problem still remains with the dense method. Here it's the time to compute the partial evaluation to compute the power of the matrix is still considerably large. And the graph structure of the artificial symbol 1 is the cause of the problem, that we take more time in computing the power of the matrix with the dense format. And it's also highlight the importance of the sparse representation because we can see that the program matrix usually very sparse. So next, going to the conclusions. So we have proposed to improve the linear algebraic approach for abduction by employing the partial evaluation. And partial evaluation step can be relied as a power of the reductive abductive matrix in the language of linear algebra. It's significantly enhanced in terms of execution time, has been demonstrated using FMEA-based dataset with both dense and sparse representation, but actually especially more with the sparse format. But maybe people wonder why do we need the linear algebraic method? So actually we can see that it simplifies the core algorithm. It's easier to understand and easier to implement. And it also can take advantages of recent advancement in tensor-oriented computing hardware. And it's expected to be easier to implement in parallel and better scalability. And in the future, we expect to do more with this topic. First, we try to handle loops in the program and extend the method to work with non-hard clauses. And we also try to employ an kind of effect prediction to know better when to apply partial evaluation and how deep we do unfolding before solving the problem. This is maybe one of the most interesting and difficult problem. And moreover, we try to incorporate more efficient planning techniques on knowing where we should zero out the, we zero out the matrix, the abductive matrix, so we don't need to compute that branch. It's also maybe a potential topic. So this is a reference. So if you are curious, you can see our previous publication here. This is ICT AI. And this is the end of my talk. So time for question and answer. Thank you very much.
Questions?
Yeah, please.
Can you talk a little bit about how this would be applied to, accelerators like graphics programming units or tensor units? So my understanding is your second from last slide, you talked about how that's an advantage. You can use acceleration hardware.
Yes.
Right, but that have you actually tried that yet?
We actually not yet focus on doing like acceleration, like implement it in GPU. Okay. But actually now there are so many BLAST library that support it. So it's the problem with our current problem is like we have to solve the minimal hitting set problem in the way to solve the abduction problem. So for minimal hitting set problem, it's as far as I know, like it's not really efficient to solve in GPU. So we currently have not yet considered kind of GPU implementation of the method.
Okay, is
but
that because
it probably can be, yeah.
And why is it? Is it because the matrices are too big, or is it because it's too sparse, or not computationally intensive enough?
I think it's because of the basic nature of like permutation problem or like a set problem. Maybe I'm not really sure, but in solving minimal hitting set problem, it's not easy to how to say like doing in matrix, like linear, like the answer and do and compute it in the same way. So it's not easy. So not yet. Maybe some people can do it, but it's not really efficient. Yeah.
Thank you.
Other questions?
Please.
Thank you for your talk. My question about so you use the PySat?
Yes. Yes.
The inside.
Yeah, for enumerating the minimal hitting set.
Okay. Enumerating what?
Minimal hitting set.
Minimum hitting set.
Yes.
Okay. But PySat is just a Python interface of SAT solver. So.
Yes.
So, what do you really use by using PySat?
No, we just use this for solving the...
I know, but
yeah.
But the backend SAT solver or backend algorithm for enumerating.
Actually I just forget it, sorry. But yeah, I just use the default PySat minimum hitting set enumerator, and the base algorithm is For now, I cannot.
It's okay,
yeah. Maybe we can.
We can talk later.
Yeah.
But my one more question about maybe you can instead the ASP can be used for enumerating.
Yes.
Okay.
Yes, I think ASP can do that.
Okay. Thank you.
Other questions? No? Okay, it's time to conclude, to finish this session. So let's thank speaker again.
Thank you very much.